Hi everyone, I am Narusha Isaacs Klein. I work for Bricks and Idea. I was also part of the team that was creating resources and teaching the data analytics training. Um, Today we're going to be focused on statistical analysis. So this is just a brief overview of what's going to be covered in today's presentation, as well as the Jupyter notebooks that you were shared in the week 2 folder. Okay, so today we're going to explore some of the most powerful Python tools used in scientific computing and data analysis. Python has become incredibly popular because of its open source, meaning it's free and constantly improving by the huge community that uses it. It's versatile and integrates well with many libraries, making it ideal for anything from simple data cleaning to complex machine learning. We will specifically focus on 4 key libraries today, which is the pandas for data manipulation, NumPy for numerical computing, SciPy for advanced statistics, and stats model for statistical model. These tools work together seamlessly and help us analyze and understand data efficiently. There are other tools available within Python, but we won't be focusing on that today. So let's start with NumPy. Think of NumPy as a foundation of scientific Python. It provides us with a powerful data structures such called arrays, which is basically a list, but in a much faster and more efficient way, especially for numbers. NumPy allows us to perform complex mathematical operations much quicker, such as matrix multiplication and generating large random number or data sets. Many other libraries, including the pandas and SciPy that we will be discussing, was built on top of NumPy because of its speed and reliability. If you are working with large data sets and need heavy mathematical computing, NumPy is quite essential. Then we have pandas, which is built on NumPy, as said before, but designed specifically to work with data structures, such as spreadsheets, tables. Pandas introduces us to something called a data frame, which is just a two-dimensional table which has rows and columns with variables, and this will be explored once you see the notebooks. With pandas, you can easily load data from many different sources. You can clean it by handling missing or duplicate values, filter through the data to focus on specific and important columns. You can transform it by adding new columns or aggregate the information that's within the data. And since data cleaning and manipulation often takes up majority of data scientists' time, pandas is an indispensable tool. Next, we will be focusing on SciPy, which builds on NumPy and adds a vast collection of scientific algorithms within it. It's especially powerful for statistics, optimization, signal processing, and solving differential equations. In statistics, SciPy provides functions for hypothesis testing, probability distribution, and descriptive statistics. This means you can test if the difference between groups are real or due to chance, model data distributions, and much, much more. SciPy helps bridge the gap between raw data and meaningful scientific conclusions. And then we have stats model. While SciPy is great for many statistical functions, stats models specializes in building and evaluating statistical models. It lets us perform regression analysis, hypothesis testing, and diagnostics checks. For example, if we want to understand how one variable influences another, like how stars' distance affects its brightness, stat model helps to quantify the relationship and assess the significance. It provides detailed outputs, including coefficients, p-values, confidence intervals, which is crucial um, for interpreting scientific results. Um, for workflow integration, one of the biggest strengths of these libraries is how well they work together. A typical data analysis workflow might start by loading and cleaning data with pandas, performing numerical operations with NumPy, and then conducting statistical tests with SciPy, and finally building predictive models with stats model. This integration means that you can handle your entire analysis in a pipeline within um, a Python environment, which also reduces errors, making your work reproducible and easy to share with anyone. There are other packages that you can use within your notebook and run it seamlessly within Python. And that's why Python is widely used within academia also. Then we have real world applications, and these are just a few of the tools that it's been used, field that it has been used in. These tools are widely used across many fields. We'll just focus on astronomy, biology, and finance, for example. So in astronomy, for instance, researchers use pandas to clean star catalogs or any catalogs of data, and SciPy to test different groups of stars that have distinct properties, and then use that model to model relationships between two variables. Similarly, in biology, pandas manages large data sets, and SciPy performs statistical tests on the gene expression, and stats model would predict the outcomes of this. In finance, time series model from stats model is often used to forecast stock prices and predict trends that might be coming up. So these are just a few examples of how versatile and essential these tools are and how they can be used in real world problems. So, in conclusion, Python scientific ecosystem, specifically the four that we mentioned today, provides a powerful, flexible, and integrated environment for data analysis. So, whether you're cleaning data, performing statistical tests, or building predictive models, these tools empower you to focus on the science rather than the programming because of the packages that it already has. Um, you can use many different packages to speed up the process of you having to code everything from scratch. There's many packages available since it's open source. Many people keep contributing to the packages, and if you want, you can create your own package as well. Um, then I'd be happy to take any questions now, and then we'll work on the actual notebook where we'll look at practical examples of the tools that I just explained. And that would be more hands-on, and I'm happy to discuss anything that you have to ask. Thank you.
Okay, we've got, hi Narisha, this is Sally speaking to everyone in the room. We've got some questions on the chat. The first question we have is, do we have to do all the questions given in the exercises? So, general question to start us off.
So it's advised that you do the questions. We advise that you put, if you are struggling, put the questions in the Slack channel and start a discussion around it. That way you learn better. Um, it would be more helpful if you actually work through this so that in the next coming weeks, um, when you build on the skills that you're supposed to have learned in each week, it becomes easier. So if you are struggling, I suggest you put it in the Slack channel and we can have a discussion there. It's not a test, so don't feel stressed out about the questions. It's just to help you learn because you learn while you're busy with practical examples.
Okay, and how can we perform statistical analysis from scratch without using any of the open source libraries?
So that would mean that you would actually have to code each and every equation or like go to the very basics. So if you, let's say integration, for example, you'd have to code it from scratch, from the actual equation, each variable, set the limitations, etc. So if you don't want to use the libraries, you can code it from scratch, but then you'd have to code every single bit on your own.
Okay. How can we perform statistical analysis from scratch without using, oh, that's the one we just answered, sorry. Next question, why use SciPy when there's stats models?
So SciPy has different built-in operations compared to stats model. SciPy has different values that is stored within it, and stats model is basically just for modeling. Stats model would then also be very useful for regression lines, least squares, those sort of things, and modeling itself. Where SciPy, you can use it to call variables and if you want to look at the documentation of the differences between the two, I can send the documentation for each one.
Yeah. We have a comment rather. The questions are not difficult, but too many.
Okay, I understand. Okay. Thanks for letting us know.
Um, then they go on to say, so if we have already have the basic to intermediate level of Python skills, can we be part of any projects related to data analysis? If yes, where can we find such data? That's the last question in case you want to read it.
So you're saying outside of this course or within the course? Because we do have the capstone projects that would be coming out. Um, and then you can be working on those projects in itself, which would be more important than the homework questions. Or do you mean projects outside of the course that we have currently?
Okay, you
Hello, good evening, madam. Now,
go
may I
ahead.
speak?
Yes. This is the person who asked the question, Narisha.
Okay.
Yes. So, good evening, ma'am. I wanted to clarify that since you asked, I wanted to ask you if you have the sources of any sort of data analysis provided within the course, and if not, then I'm also comfortable in using data that is outside of the course as well. If you have any suggestions of, obtaining that kind of data, that is
Sorry,
what I wanted to ask.
I'm not entirely sure I got what you meant by that. Can you repeat yourself quickly, please?
Ma'am, I wanted to clarify that will we be getting any such data analysis like or real-time data analysis apart from those already given in the exercises, or do we have to approach somewhere else? Like you said that there would be some other projects being launched as well. So wanted to
Yeah, so
clarify whether we have.
there will be something called the capstone project. that we'll be giving out soon, and you'll work through this project throughout the course. Um, and you whatever data is needed for the capstone project, you will be given.
Okay, ma'am. Thank you, ma'am.
Pleasure.
I think there are also various citizen sciences. If you're interested in working with different data yourself, or trying different data analytics routines on real science data, there's various fascinating citizen science projects that you can get more experience as well, even outside of professional astronomy. I'll try and put some links in the Slack as well for those citizen science projects that you can work on.
Ma'am, again, one more question. Ma'am, for these citizen science projects, do we have to cold mail the professors directly, or are there some other common forums where we can approach?
Oh no, this is common program. So you don't need to approach the professors, just mainly the organizers, or usually there's I know there's projects that involve, there are some in the past that involved radio astronomy science data, and basic yes, so I think that's a galaxy identification. There's also citizen science projects involved with the Zooniverse projects. That's not just astronomy related, but all sorts of sciences. I know one of those projects is, for example, searching through multiple images of the sea, for example, to see if there's any stranded people, and it's just something that um, we don't have the capabilities technology-wise, so any bit of help works out for that. I know it's quite an incredible sounding project, but that's with Zooniverse. So I'll try and post some links to that in the chat.
Thank you, ma'am.
Okay.
If there are no additional questions, I will just briefly go through the notebook. Okay.
Okay, no other questions.
Okay, so you would have gotten access to the week 2 folder. There is a folder called data, and all the data that is needed for this specific week would be in this folder. There is a basic NumPy code where they just give you basics of NumPy, arrays, how to handle them. So you can go through this one on your own. If you have any questions, you can post it in the Slack channel. And then there's also a basics of pandas. You can also go through this on your own and just read through this where they have the key information, key words. This is how the data frame looks, where you have the columns and the rows. Just gives you basic information on pandas itself. And then what I'm going to be focusing on is the stats, data cleaning, filtering, and basic statistics for today. We will be using Gaia data. Here's a brief overview of what it is, where it comes from. You can do more research if you want. And then here's just some information on the key terms that we will be using. So data frames is just a powerful way of storing data, which is usually CSV files. And it's just a spreadsheet or table. It has rows and columns. Nans is referred to missing data. So within the scope, a 0 is not represented as a missing data or missing value, because 0 is actually a value, but a nan would be considered missing values. And then we'll be talking about filtering, how you can do that, vectorization, basic statistics, correlations, and plotting. We will be discussing plotting very briefly, because next week there's the visualization week, which would go into detail of how to plot and what to call. So firstly, importing libraries. These are the libraries we're going to be using. So you can import it and give it any name you want to. So pandas is just called in, and you can call it whatever you'd like, whether you want to call it PD or P, anything that's easy for you to remember as you're coding. If you don't remember, you just scroll back up. Then there's NumPy, which is NP. SciPy stats. We're importing stats from SciPy. And then stat model, which is SM, which will be used further down. The first thing we do is load. So DF would now be our data that we're loading. And that is called in using pandas. And it's reading the CSV file, which is located in the data folder. This is just to load the data itself, and then this shows you the actual data. So just to print the data and show it in a clean format. So you'll get the source ID, the RN deck, which is just the position, etc., etc. And then this is all the information that's in the data table. So as we move down, something called data cleaning, which removes either problematic values, which either doesn't make sense, such as negative distance, for example. You can't have something called negative distance. But more importantly, something that has missing values, which is missing nan values. So you can remove these empty spaces. So after cleaning, we are left with a certain amount of data, having removed everything that has a specific nan value associated with it. You can remove nan values, you can remove negative values. You set what you would like to remove. Then data filtering, which means you focus on a specific data set. For this specifically, in astronomy, we want to focus on, let's say, bright and nearby stars. So in our data, we have the G magnitude, which we know if the G magnitude is less than 5, that means it's bright. And then we know if that the parallax is greater than 2, that it will have a nearby star. So what we're doing now is we're just filtering the DF data frame that we imported, which is this, and we're calling it filtered DF, which means we'll only choose the ones that satisfy the conditions that we set. So when we choose DF and whatever is in these square brackets, we're choosing a specific column. And in that column, we're choosing every star that has a magnitude less than 5. We then move over to parallax, and we're choosing every star that has a parallax of greater than 2. We then save this into what we now call filtered DF, which is just the filtered data frame. You can do this with any amount. You can choose it to be a magnitude of 10, a magnitude of anything you set it to, especially if you have your own data sets, maybe not astronomy specifically, a data set that is related to the work that you have. You can set the parameters that you want to work on. and choose what is relevant to you. That's just called filtering. And then we're going to discuss how we add a new column. A new column is any data that you want to, that is related to the information that you already have. So one simple way is if you converting or calculating with the data that you already have. So in this case, we converting from parallax distance to parsec distance, and we'll add this column in. You can also calculate various things using the magnitudes, the distance, any of these columns, and then after calculating, you can add in a column. Here, where you see this in square brackets, this is what you are giving the title of that column. So if you see at the end, we have now added this column, which is called distance PC, which is just distance in parsecs. And everything that we've calculated would now go into this column. We have taken these values over here and calculated to get you these values, and they are related to each other. So each one in, let's say, row 10 would be calculated and saved in still row 10, but in the new column. So that's just how you can work with the data frame itself, adding columns. And then we have the basic statistics. So a summary of statistics that we all use is mean. So that's just the average. So you choose a column, any column you want, and you can get the average value of all the stars in that column. So once again, you choose the column and define it here. And then you just say dot mean. The open brackets means all the values in there. You can do the same with median. This means the median of the parallax, because we chose parallax column. And then the last one is the standard deviation. And we just say STD. And you can get all these names from within the statistics. So then you can call on anything that you need. So that's just the basic statistics. We then have correlations, which just tells us how two variables are related to each other. How, if the one is increasing, does the other one increase, or does it decrease, how they relate to each other. In this specific case, we are relating parallax with parallax, which would give us 1, meaning they are exactly the same, they lay on the exact same line. Then we have the magnitude versus parallax, magnitude versus the PMRA, each one related to each other, and that's how the values here is calculated.
Sorry,
And
Nerud. Just a
sorry.
quick question. While you're at the section, could you please mention the unit of parallax here? One of the questions in the audience.
So this is just the parallax value. We're not using the distance that we calculated in parsecs, but we can say distance in parsecs here if we wanted to change it up. Does that help? So it's just distance in parallax.
Okay, yes. Thanks.
Pleasure. And then, yeah, so that tells us the correlations. And then something that I said would be described better next week is we import something to plot. So there's matplotlib and various other packages like Seaborn, etc. That will be explained next week. But here's just an example of how important plotting is, because then you can visually see what you're working with. This specifically is just the magnitudes and how much of each star falls in a specific magnitude. So here we can see that in the 15 magnitude, we have the highest number of stars. Um, it dies down as we go to lower magnitude values. Um, Here you see the bin size, which just says how many values are binned into a specific category. So if you were to increase this, the blocks would be much larger, because now more of them are binned together and they're binned in a specific region. So, for example, this is the range that it's binned into. If you were to increase the 20 maybe to 40, this would be all of these binned together. But like I said, it will be explained better next week. This is just an example of how you can plot to see the distributions of, let's say, magnitudes or distances or anything like that. Now we have hypothesis testing, specifically with SciPy, which can also be with other packages. They ask, do bright stars have different, which they're saying is bright stars with a magnitude less than 15, have different average proper motion, which is the PMRA, than faint stars. So the faint stars is greater than equal to 15. So now they're calling some set of values bright. So we choose all the bright stars, and for that the conditions are met to have all the bright stars greater less than 15, and they're saving the proper motion, the average proper motion from that set of data. So we're calling it from the original data frame. And then we'll choose the faint stars, which is everything greater than equal to 15. Here's where the statistics part comes in. T-stat is going to give us the t-statistic value. And then the p-value would be what we get out from this stats test. You use the bright and the faint to compare to each other. And this is the bright value, the PMRA for the bright values, the bright stars, and then the PMRA for the faint stars. We then set so this would print what the values is, what the t statistic and the p value is. But then we do this if statement, which basically tells us the significance of this p value. You can do it for the t value or the p value. So we specifically looking at the p value, which in this case we set it to 0.05. If it's less than 0.05, then it would mean that there is a significant statistical difference. But if not, it means that there's no significant difference found. Here you can see the value that we found is 0.79, which means there's no sort of significant difference. Here is something that you can read up on. I'll just go through it very quickly, but it gives more definitions on what I already explained. These are independent two samples to test. As you could see, they are independent because this would be all the bright stars and this would be all the faint stars. Interpreting the results, you can set this to anything you want. So if you working with your own data set and your level of significance is up to 0.5, you can set that value to 0.5. So if anything falls within that, there is a significance. If not, it will fall outside. Obviously, the lower the value, the more significant the relationship is. So you can just read up on all the definitions there. Then we go to stats model, which is going to be using a simple regression. We In this, they ask us to predict the G magnitude using distance. Here we'll be performing a simple line regression using the stat model library. We now use the distance actually in parsecs and relate it to the G magnitude. So this is just calling the column that we created with the distance in parsecs. And this part itself here, where sm dot add constant is adding a column of ones to this x that we are calling here, which is called the intercept or constant term in the regression. That would be our x. Then we define the y. So we are comparing the magnitude and the distance. So we have to call the distance column as well. Now we want to model what we have called in, which is the x and the y. In this case, we're using the ordinary least squares. There's many different ways in which you can do it, and you can call all the different modeling methods, the fitting methods. This specifically fits a straight line to your data, which is if your data runs in straight line, that would be most sensible. But if you have an exponential, or if you can see your data clearly follow a different shape, there are different modeling methods. In stats model itself, you can check the documentation of that. I can send you a link for that. But in this specific case, we'll just use the ordinary least squares, and this dot fit does the best fitting to the data. And then the last line we do is the print model. So printing the summary of all the answers that we get out. So we'll get the coefficient, which is just the slope and intercept. We'll get r squared, which is just how well this line fits in our data. So if you have a broad scatter, this r squared value would probably be quite high. The r squared would not be very well fit. Then we have the p-value, which is just the statistical significance, and we'll get standard errors. Printing the model summary would give you this table. You can get all your information that you need, the constant, which is, if you look at the straight line, you normally have a y-intercept and a gradient. That's what you get here. You can plot this as well using the values that you get and the errors accompanied with it. The R value is normally ranging between 0 and 1. 1 means probably it's really well fit, which means that the data sits almost on the line, which is almost never. So you'll get something close-ish to 1. Standard errors. Then we have some technical terms, which is just the regression, which was already explained, but you can read up more on this. And if you have any questions, you can ask them. We do have some homework exercises after this, which you can go through. And like I said earlier, propose any questions in the Slack channel. If you're struggling with anything, put it out there, and we can help you answer them. We can start a discussion with the fellow participants, whoever wants to participate in the discussion. It helps. Here are some resources that you can use, but if you want any extra or specific resources, I can send you links to documentation, or you can just Google it because everything is available on Google. But if you want specific things that might be just easier to ask, you can ask in the Slack channel. We then have the descriptive stats, which is just advanced. I'm not going to go through it because once you've gone through all of these, you can then go through descriptive stats. This is more advanced and not necessarily needed, but if you are someone that's going to go into something in this field, it's highly recommended. It has all the definitions and more mathematical, um, more in depth. You'll have more caution displayed, how they work, how they affect each other, etc., and how useful it is. So you can go through this notebook itself and has all the explanations of standard error, standard deviation, etc. Um, but I'm not going to go through it right now. But if you have any questions of it specifically, you're more than welcome to ask. And then this is just a table that's created within one of these notebooks. In Panda's notebook, it's created and saved here. So that's all from my side. If you have any questions, I'm going to be taking questions now and having a discussion on anything that you need. I'm going to stop sharing, otherwise I can't see the question.
Okay, Narusha, we've got a question. Does the data frame consist of data for each star? And then if yes, could you please explain why we are saying it is the average proper motion?
Sorry, wait, I missed what you said there for a second. What did you say, Sally?
Does the data frame consist of data for each star? And then if yes, could you please explain why we are saying it is the average proper motion? It was, the question was asked at 6:34.
Okay, so it has the proper motion for each one, and then we calculate the average. So there's individual stars for each row, and then we'll calculate the average, if that makes sense.
What would be the sample proportion for such a data set, which would be essential in finding the p-value?
What would be?
So it also at 6:34.
I'm trying to think what the person mean. If you can unmute and explain what you mean by the sample proportion for such a data set. What do you mean by that?
Yes. So I think in the meantime, maybe Parth, if you could just put your hand up and then we could see that you're ready to speak. I think in the meantime, we'll go to the next question. There's already an answer for this, but what data would be dot mean brackets method retrieve exactly? What data would dot mean brackets method?
So it will calculate the mean or the average for all the values in that column.
Parth has got their hand up. So Parth, you can unmute. And ask your question.
We can't hear you, so you just need to turn up a bit.
Hello.
Yes, we can hear you.
Yeah, so I was saying sample portion is kind of similar to the mean. So like if you have a survey of people saying yes for something, so if you have, for example, n people and for example, let's say q people say yes to that, so q is the sample proportion. Uh, so like for example, in this case, if you're taking the brightness of all stars in a given survey. The sample proportion will be the average of that.
Can you repeat yourself? I didn't get the whole
So if you have a
first part.
sample, if you have a sample of brightness of stars,
Okay.
the the uh, the mean of the absolute brightness of stars will essentially be the sample proportion for the given distribution, and then you find out the error, and then using that you find out the p-value depending on the t. Like for example, if you have a t distribution, then it'll be a bit different. But if you're using normal distribution, then you can just use the phi values and then calculate the p-value.
Yes, you can. You can calculate the p-value from that as well.
Yeah, so I was saying in this data set, what exactly would that mean value be?
So I don't have the value, but you can calculate it.
Okay. Or also, where can I get access to the data set?
It's also in the GitHub folder, um,
Oh,
where you have week 2. If you can't find it, I can try to just explain how to get to it.
no.
If you can try now, and then if you can't find it, I can just do a little tutorial on how to find it. I'll also do a little tutorial on how to join Slack channels and how to use Slack.
Mhm. I have, I think, already forked the GitHub, so I'll go through that and like try to find it. If I don't, I'll probably put a comment on the Slack if I have any difficulty. Thank you.
Okay, later.
We've got a question. We'll come back to the question. Pranjal, yes, you've got, maybe if you can speak, because your question was next. I was going to read it out. So maybe you can say it yourself since you've got your hand up. This is a question at 6:37 starting.
Am I audible?
Okay, Pranjal, we can hear you. Please go ahead.
Yeah, I had actually two questions. The one related to the one I asked before, is that the PMR, the average proper motion that was calculated. I'm sorry if I missed this, but was a mean taken for each column?
That would be the mean, and the average is the mean of that specific column. So it would be, if you say dot mean and just have open brackets with nothing inside, it would take the mean of all the stars. But if you select specific stars, it will only give you the mean of those specific stars. So you can select according to either you want the brightest stars, and then you can filter it through that, or you can say, okay, let's only take rows 1 to 10 and then get the mean of that. Or, well, you can call it the average or mean, doesn't matter.
That means like we are first filtering like magnitudes which are less than 15 and then taking the mean basically for to calculate the PMRA.
Yes.
Okay, thanks a lot, ma'am. And the other question that I had was, uh, as far as I know, the intensity of the stars that we observe, as it is basically light waves, follow an inverse square law, and the magnitude, while calculating the magnitude, we generally take a log. So is the linear regression model, will it just be an approximation? Would it be a good fit? That was my question.
So if you're saying if it's a log, would a linear regression be the best fit? You can use the log fit as well. Um, it would be best if you plot your data and then see what shape it follows. But if you're saying that one of the data sets is log and one is not, or is both log? I didn't catch that part.
No, since like for example, I actually did a simulation before while I calculated, plotted the uh, magnitude of stars in the histogram, like not from any particular data, but just a simulation from the theoretical distribution of stars. It was actually kind of a logarithmic in one of the axes. So
Okay, so
I thought, yeah.
you can either plot a logarithmic regression, or you can use np dot log 10 and convert the distances to log distance, and then the linear regression would help better. Does that make sense? So you'll take one of the data sets and then you'll and then the linear regression would fit better. But either way, the best fit line is always an approximation.
Yeah. Thank you so much, ma'am.
Okay. Thank you for the questions, of course. Let's just see. I've got the other questions here. Okay. What is the standard value that shows that the p-value is statistically significant or not?
So generally, you can set this according to what your data is. Generally, you'd say 0.05. You reject the hypothesis if it's less than, greater than. So in that, I showed you that there's 0.05, which just means it's a 5% chance of being true. So you can set the value to 0.01, 0.02, depending on your data set itself. For this specific data set, we set it to 0.05, which we then said if there is the statistical significance for that. Let me just. Okay, I don't have to share because you have access to this notebook, but there would be no significance if it's a value greater than 0.05. But if it's less than 0.05, we classify it as having a statistical significance. So it all depends on the data that you're working with. The specific data that we're working with, we set that threshold.
Okay. Someone has asked, please give a tutorial on how to access Slack and the library. I'm going to put a link relating to how, if you need to join the Slack workspace, I'm going to provide you with a link now. But Narusha, I believe you're going to show how to access, if you can show how to access the library, maybe, or I guess maybe, and I think that means GitHub or, yeah. Or just show general how to connect to a channel. I think that's probably a good demonstration. But we can do that maybe after the questions.
Yeah, I think that would be best. I can show them how to use Slack itself. And then if anyone is having troubles getting into GitHub, please do add that as a question. And then I can also show you just how to get to the GitHub itself.
Okay, what does that .ds store file do under week 2 directory on GitHub? And when does it get created?
Let me just check. I haven't seen it, so I'm just checking the file itself. I know that .ds store normally stands for desktop services.
But it's not a crucial element to the assignments in any case.
No,
I think
it's not.
It's the auxiliary. It's an extra file that GitHub uses or creates during when files are created. I think maybe someone in the room knows that a bit more, but I don't. It's not needed.
It's not necessarily needed. It usually is just. It's just if it gets created when you open a folder in Finder, which is on a Mac laptop, but you don't actually need it, so it doesn't need to be there. If you don't need it, it's not. If it's not there on your side, it's not going to change.
Oh, someone actually said that it's a config file that was created by Mac, as you were saying, to store visual information in the folder. Okay.
Yeah.
So we sorted with that. Okay.
The data frame. Okay, we already went through that.
Also, we consider two-tailed hypothesis, right? Or circumstantial. That's what
Where?
was at 1851.
Okay, I'm just finding the question. Just give me a second. Is this after the GitHub and those
Yes.
questions?
So it's 1851. So
Oh, okay, I
it's
see, I see. So you can consider one tail or two tail. The short answer would be it depends on what you're trying to detect or prove. And it would be circumstantial based on what hypothesis you have. So for two-tailed test, it has any significance in either direction, which you don't have before. Um, for example, how do I? For this example, we use two-tailed, but you can use one-tail as well. Because then one tail means you moving in a specific direction of difference. With two tail, it could be either way. So it opens up more. Two tail is where you're checking the differences, any differences, and one tail basically is for increasing or decreasing only. If that helps.
Okay. There was a question, but they're going to take it the discussion. You can see the question from Pranjal. He might have asked it earlier, but they're going to take the discussion through to
Slack. Yeah.
and then there's
Okay.
just a question just come up now. So the last question from Jayton.
Okay. If I'm using Spider to work on exercises on my local baseline system, I want to. So you would like to push your work to your own GitHub? Is that what you're asking? The submission for exercises would be on the monday.com form that was sent out. So you don't have to push it to GitHub itself. And then I can view week 2 materials, GitHub. Okay, so I'm going to give a small little tutorial on how to use the GitHub and Slack. So, Sally, do you think I can do that now, or is
No,
there
I
more
think you
questions?
can go. Yes, go ahead.
Okay, let me do that. Um, okay, let me just share my screen. So most of you would have access to Slack itself, which would look like this. So you would have general access to this Allbricks idea data analytics program and all the other channels you'll have to join yourself. The way in which you can join a channel is sometimes this is not showing, but you click on this arrow over here and you get all the channels. Then when you go to add channel, you don't say create a new channel, but rather browse channels, right? So then all the channels that is available to you would show you. So you'll have, and this one, which is required, it's just the general channel, everybody is there. Then we have a general discussion channel, which you can join. As you can see, I've already joined it. I can leave it at any time. And then For example, this is week 3 data visualization. I have not joined this channel. And if I want to join it, I will click join over there. And then I would be part of that channel. How to navigate the channels that you already have is you go back to the home, which is this little house in the corner. And then if it's not drop down, you can drop down and you can find all the channels that you have joined here. Week 1, you can ask all your week 1 questions. Week 2, you can ask all the week 2 questions. In here, I've also shared the presentation that I've completed. You can also go back to questions that other people has asked and see what was replied. And sometimes there's some useful links. And you can see if you need to add, if you have any information for these people, and ask, have a discussion, and then help one another. And yeah, that's why it's always encouraged. So when you're busy with your homework assignment, maybe we can post question 1, blah blah blah, and then post the question and then start a conversation. How to reply to a specific message? You say reply in thread. That would be starting a thread of a specific question and then not just adding it in the general channel. Additional help, you can post it here if you can't access any channels, and then I will assist you from there. Now moving to GitHub. So in week 2, I think the link was shared. Let me just see where the link itself was shared. Okay, so the link was shared in All Bricks Idea Data Analytics program. So here you have this message from Lebo, and you can go, these are the links to the Zoom, and here's the materials. So you'll click on this and it will open this, right? In week 2, you have another folder called data, and that is where you'll find the data used. Then you have each notebook and the other data that's needed. So if you're struggling within GitHub to find these and it's not showing up on your side, once again, just send us a message and we'll try to figure out why yours is not showing up or why you do not have access to it specifically. So we aren't using any of the paid for add additionals. So you can sign up for free. You don't have to pay for Slack. You can sign up. The Slack link Sally has already shared. Let me reshare this link itself. If anyone is still not able, you can try to join through that link. If you can't, please message us and then we can get you access. Has everyone managed to find the data in the week 2 folder? Okay, for GitHub, let me just get the link. Does anyone have any other questions? Can everyone access GitHub and Slack?
So there's
What
a
do you
question. Yeah.
by download the materials on GitHub? Do you want to download the notebooks and all the materials itself?
Yes, Narusha, sorry. Good everyone. Thank you for your time and efforts, and thanks to the coordinators. I'm actually having problem trying to see where exactly to click to download the materials. I can actually view all these things GitHub. I can see them, but I couldn't see the icon to click to download them so that I can actually practice them offline. So if you could also do me kind to show me maybe from your end where I can actually click to download them.
Okay, so if you go
Like
onto
a zip folder where I can get
GitHub
everything. Yeah.
and you go
Yes.
right down to the README file,
Maybe do a demonstration.
load.
Share your screen, if possible.
Okay, let me show you my screen. So if you, sorry, just waiting for this to move. So if you go to, we were in week 2, and you scroll right down, at the bottom you have something called the readme.md or precourse.md. Here is a very descriptive way of how to get all the data and everything that you need, but specifically the data itself or the notebooks. You can go to git clone and then clone the entire repository. So this week 1 and week 2. So you can use this information here in the readme.md file. Does that help?
I think there may be some confusion about where to write that in order to download the file. So, for example, someone who's maybe used to Windows, where you just right click and download, it might be a bit confusing the using some sort of terminal or yeah, maybe you could explain that.
Okay, so that is in the terminal, but if you want to download each notebook, you can go to the notebook itself, and there's this little arrow that you can say download, and it will download this entire notebook. So you can do that as well. If the code that you put in the terminal just downloads everything all at once. But now if you go to each one, you can download them using this little icon over here. So if you click on any of these, you can just click on it, download. If you go to the data itself, just let me go back. And then you can download that as well. Let me just find it.
Oh, there's a comment as well. I think he just wants to download the whole repository as a zip directly from GitHub.
Have you used the terminal before? Because then you can just put that in the terminal.
Okay, otherwise, maybe we can take this discussion, if you're able to get onto Slack. Please post your question in the Slack, and someone's just written, in Unix systems, terminal is the only choice, but in Windows Windows GitHub desktop client may be used, I think. But perhaps we should take this discussion to the Slack channel, and there's a technical channel that this question can be posted, and then we can maybe assist offline further. Yeah. Narusha?
Yes.
Otherwise, I don't think there's any other questions. Are there any other questions in the room?
Any questions, comments, any of that sort? If you can't think of anything right now, you're more than welcome to post it on the Slack channel. And if you can't get access to Slack, email any one of us and we'll get you access to the Slack and help you from there.
I don't
Okay.
see any questions. Yeah, so I think we can finish
Thanks
up.
everyone for attending. Good luck and enjoy. If you have any questions, your capstone project will be coming out soon. Thanks everyone. Bye.
Thank you all.